Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the depths of a South Dakota gold mine, 100,000 gallons of cleaning fluid sat in darkness, waiting to catch the universe's most elusive particles. This was the Homestake experiment, and it would reveal one of physics' greatest mysteries. The year was 1968, and Raymond Davis Jr. was hunting for something that barely existed: neutrinos. Neutrinos are the universe's ultimate escape artists. Born in the nuclear furnaces of stars, these ghostly particles stream through space at nearly the speed of light, passing through entire planets as if they were empty space. Every second, trillions of neutrinos from our sun pass through your body without you feeling a thing. They are electrically neutral, nearly massless, and interact so weakly with matter that they can travel billions of light years without being stopped. The story begins with Wolfgang Pauli's desperate hypothesis in 1930. Physicists had discovered that energy seemed to disappear during certain nuclear reactions, violating the sacred law of energy conservation. Rather than abandon this fundamental principle, Pauli proposed that an invisible, nearly undetectable, particle was carrying away the missing energy. He called it the neutrino, Italian for little neutral one. 26 years later, Frederick Rines and Clyde Cowan finally detected these phantom particles near a nuclear reactor in South Carolina. Their discovery confirmed Pauli's audacious prediction and opened a new window into the universe's hidden machinery. But the real mystery was just beginning. When Davis began his underground experiment, he expected to detect a specific number of neutrinos streaming from the sun's core. Nuclear fusion in the sun's heart converts hydrogen into helium, releasing tremendous energy and producing electron neutrinos as byproducts. Theory predicted that Davis should detect about 1 neutrino interaction per day in his massive tank of perchloroethylene. Instead, he found only 1/3 of the expected number. This wasn't experimental error. Decades of careful measurements confirmed the deficit. The sun appeared to be producing far fewer neutrinos than nuclear physics predicted, or something was happening to these particles during their 8-minute journey to Earth. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The solar neutrino problem, as it became known, sparked a crisis in physics. Either our understanding of stellar nuclear processes was fundamentally flawed, or neutrinos possessed properties we hadn't yet discovered. Some scientists questioned whether the sun's core was cooler than expected, while others proposed more exotic solutions involving magnetic fields or axions, hypothetical particles that could convert neutrinos into undetectable forms. The mystery deepened when other experiments confirmed Davis's results. The Kamiokande detector in Japan, originally built to search for proton decay, was modified to detect neutrinos from the sun. Using 800 tons of ultra-pure water surrounded by sensitive light detectors, Kamiokande could identify the faint flashes of light produced when neutrinos occasionally interacted with water molecules. Kamiokande's results were stunning. Not only did they confirm the neutrino deficit, but they also proved that these particles were indeed coming from the sun's direction. The detector could track the neutrinos' paths, showing they arrived during the day when the sun was overhead, and continued arriving at night after passing through the entire Earth. This detection method revealed something remarkable about neutrinos: penetrating power. While sunlight is blocked by Earth's solid bulk, neutrinos pass through our planet as if it were transparent. The entire Earth is less of an obstacle to neutrinos than a sheet of paper is to visible light. This ghostly behavior would prove crucial to understanding their true nature and solving the solar neutrino problem. The solution to the solar neutrino problem would revolutionize our understanding of these ghostly particles and reveal that neutrinos were far more complex than anyone had imagined. The breakthrough came from a startling realization: neutrinos could change their identity while traveling through space. In 1962, physicists Leon Lederman, Melvin Schwartz, and Jack Steinberger made a groundbreaking discovery at Brookhaven National Laboratory. They found that neutrinos came in different varieties or flavors. The first type, associated with electrons, was joined by a second flavor linked to muons, heavy cousins of electrons. Later, a third flavor associated with tau particles would complete the neutrino family. Each flavor of neutrino was thought to be distinct and unchanging. Electron neutrinos produced in the Sun's core should remain electron neutrinos throughout their journey to Earth. But what if this assumption was wrong? What if neutrinos could transform from one flavor to another as they traveled? The concept of neutrino oscillations emerged from theoretical work in the late 1950s, but it seemed too strange to be true. For neutrinos to change flavors, they would need to have mass, something that contradicted the standard model of particle physics, which predicted neutrinos should be massless. Yet the solar neutrino deficit demanded an explanation. Bruno Pontecorvo, a brilliant Italian physicist, proposed that neutrinos might oscillate between different flavors during their journey from the Sun to Earth. If the Sun produced electron neutrinos, but one-third transformed into muon neutrinos and another third into tau neutrinos during transit. Then detectors designed to catch only electron neutrinos would see exactly the deficit that Davis observed. This theory remained unproven until the late 1990s, when the Super Kamiokande detector in Japan provided definitive evidence. This massive underground facility, containing 50,000 tons of ultra-pure water, could detect neutrinos from multiple sources simultaneously. The key breakthrough came from studying atmospheric neutrinos, particles created when cosmic rays collide with Earth's atmosphere. Cosmic rays constantly bombard our atmosphere, creating showers of particles, including muons, that decay into muon neutrinos. These atmospheric neutrinos rain down on Earth from all directions, and Super Kamiokande could measure their arrival patterns with unprecedented precision. The detector found that neutrinos coming from directly overhead arrived in expected numbers, but those traveling through Earth from the opposite side of the planet showed a significant deficit. This pattern made perfect sense if neutrinos were oscillating. Neutrinos from overhead had little time to change flavors during their brief journey through the atmosphere, but neutrinos from below had traveled thousands of kilometers through Earth, providing ample opportunity for flavor transformation. The oscillation hypothesis explained both the atmospheric neutrino deficit and the solar neutrino problem. The Sudbury Neutrino Observatory, or SNO in Ontario, Canada, provided the final confirmation. This detector used heavy water, deuterium oxide, which could detect all three neutrino flavors simultaneously. SNO's measurements showed that while only one-third of the expected electron neutrinos arrived from the Sun, the total number of neutrinos of all flavors matched theoretical predictions perfectly. The implications were profound. Neutrino oscillations proved that these particles possess mass, however tiny. This discovery shattered the standard model's prediction of massless neutrinos and opened new frontiers in physics. The total mass of neutrinos might seem negligible, but their sheer abundance throughout the universe means they could significantly influence cosmic structure formation. Neutrino oscillations also revealed the quantum mechanical nature of these particles. Unlike classical objects that maintain fixed properties, neutrinos exist in quantum superposition states, simultaneously embodying multiple flavors until the moment of detection. This strange behavior demonstrates quantum mechanics operating on cosmic scales, with neutrinos maintaining their quantum coherence across astronomical distances. The discovery earned several Nobel Prizes and transformed neutrino astronomy from a theoretical curiosity into a powerful tool for exploring the universe. Scientists realized that neutrinos could provide unique insights into cosmic phenomena, carrying information from the most extreme environments where electromagnetic radiation cannot escape. While Earthbound experiments were solving the solar neutrino problem, the universe was preparing to demonstrate neutrinos' true power as cosmic messengers. On February 23, 1987, 3 neutrino detectors scattered across the globe recorded an extraordinary event that would forever change our understanding of stellar death and cosmic explosions. Supernova, 1987. A exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, located 160,000 light-years from Earth. This stellar catastrophe released more energy in 10 seconds than our Sun will produce in its entire 10 billion year lifetime. Most remarkably, 99% of this energy was carried away not by light, but by neutrinos. The Kamiokande detector in Japan, IMB in Ohio, and Baksan in Russia simultaneously detected neutrino bursts lasting just 13 seconds. These detections represented the first time neutrinos from beyond our solar system had been observed, marking the birth of neutrino astronomy. The timing was perfect. Neutrinos arrived 3 hours before the supernova's light became visible. To optical telescopes, this timing difference revealed crucial information about the explosion mechanism. During a supernova, a massive star's core collapses into a neutron star or black hole in less than a second. The collapse creates a shock wave that must propagate through the star's outer layers, eventually causing the visible explosion. But neutrinos, with their ability to pass through matter almost unimpeded, escape immediately from the core collapse. The neutrino observations confirmed theoretical models of supernova explosions with remarkable precision. The detected neutrinos carried energies of 10 to 20 million electron volts, exactly matching predictions for neutrinos produced during neutron star formation. The brief duration of the burst indicated that the core collapse occurred rapidly, transforming a star's core into a neutron star in milliseconds. Supernovae are cosmic element factories, forging heavy elements like iron, nickel, and cobalt in their nuclear furnaces and distributing them throughout the galaxy. Neutrinos provide the only direct way to observe this nucleosynthesis process, as they escape from the explosion's core while electromagnetic radiation remains trapped for hours or days. By studying supernova neutrinos, astronomers can peer into the hearts of these stellar explosions and understand how elements essential for life are created. But supernovae are not the only cosmic neutrino sources. The universe constantly produces high-energy neutrinos through various extreme processes. Cosmic rays, charged particles accelerated to enormous energies by unknown mechanisms, create neutrinos when they collide with interstellar gas or cosmic microwave background radiation. These interactions produce neutrino beams that travel billions of light-years to reach Earth. Active galactic nuclei, powered by supermassive black holes consuming matter, likely produce intense neutrino fluxes. As matter spirals into these black holes, it forms accretion disks reaching temperatures of millions of degrees. Powerful jets of particles stream away from these systems at nearly the speed of light, creating ideal conditions for high-energy neutrino production. Gamma-ray bursts, the most energetic explosions in the universe, may also generate neutrino signals. These events, possibly caused by colliding neutron stars or the formation of black holes, release more energy in seconds than our Sun will produce in billions of years. The extreme conditions during gamma-ray bursts could accelerate particles to energies impossible to achieve in terrestrial laboratories. Neutrinos from these cosmic sources carry unique information about high-energy astrophysical processes. Unlike electromagnetic radiation, which can be absorbed or scattered by intervening matter, neutrinos travel unimpeded from their sources to Earth. They provide direct samples of conditions in the most extreme environments in the universe, from the cores of exploding stars to the vicinity of black holes. The challenge lies in detecting these cosmic messengers. High-energy neutrinos from distant sources are extremely rare, requiring massive detectors and long observation periods. The next generation of neutrino telescopes would need to be unprecedented in scale, capable of monitoring enormous volumes of material for the telltale signatures of cosmic neutrino interactions. 2 miles beneath the Antarctic ice sheet, an extraordinary scientific instrument spans a cubic kilometer of the world's most pristine frozen water. IceCube, the largest neutrino detector ever built, transforms the Antarctic ice into a cosmic particle observatory, demonstrating humanity's ingenuity in harnessing nature's resources for scientific discovery. The concept of using ice as a neutrino detector emerged from the unique properties of this frozen medium. When high-energy neutrinos occasionally interact with ice molecules, they create charged particles that travel faster than light, can move through ice. This faster-than-light motion produces Cherenkov radiation, a ghostly blue glow similar to the sonic boom created by supersonic aircraft, but with light instead of sound. IceCube's construction began in 2005 and required 7 Antarctic summers to complete. The project demanded unprecedented logistical coordination, with scientists and engineers working in one of Earth's most challenging environments. Temperatures at the South Pole regularly drop to -40 degrees Fahrenheit, and the site experiences 6 months of continuous darkness each year. The detector consists of 86 strings of sensors, each containing 60 digital optical modules, or DOMs. These basketball-sized sensors, totaling over 5,000 units, are embedded in the ice at depths between 1.5 and 2.5 kilometers. Each DOM contains a photomultiplier tube capable of detecting single photons of Cherenkov light. Installing these sensors required melting holes through the ice using high-pressure hot water. The enhanced hot water drill could bore holes 60 centimeters wide through 2.5 kilometers of ice in just 2 days. Once drilled, each hole was quickly instrumented with a sensor string before the water refroze, permanently encasing the detectors in optically clear ice. The Antarctic ice provides an ideal detection medium for several reasons. At depths below 1.5 kilometers, the ice is incredibly clear, with optical properties rivaling the world's best laboratory glass. This clarity allows Cherenkov light to travel hundreds of meters through the ice, enabling precise reconstruction of neutrino interaction events from the light patterns detected by multiple sensors. The ice's stability is equally important. Antarctic. Ice at IceCube's depth has remained undisturbed for over 100,000 years, creating a uniform, predictable medium. The detector's sensors are protected from surface weather and electromagnetic interference, while the ice's consistent temperature ensures stable detector performance. IceCube operates as a 3-dimensional camera, photographing the brief flashes of light created by neutrino interactions. When a high-energy neutrino strikes an ice molecule, it may produce a muon that travels several kilometers through the ice, creating a track of Cherenkov light. By analyzing the timing and intensity of light detected by multiple sensors, scientists can reconstruct the muon's path and determine the original neutrino's direction and energy. The detector's enormous size is crucial for catching these rare events. Despite trillions of neutrinos passing through the detector every second, only a few hundred high-energy cosmic neutrinos are detected each year. The cubic kilometer of instrumented ice increases the chances of capturing these elusive interactions. While providing the volume needed to precisely measure neutrino properties, IceCube's unique design allows it to see through Earth itself. The most interesting neutrinos actually come from below, having traveled through the entire planet to reach the detector. This capability eliminates background noise from cosmic ray interactions in the atmosphere, which primarily come from above. Neutrinos detected traveling upward through Earth must be genuine cosmic messengers, as no other known particles can traverse our planet's bulk. The detector operates continuously, automatically recording potential neutrino events and transmitting data via satellite to laboratories worldwide. Sophisticated computer algorithms analyze the light patterns in real time, identifying interesting events and alerting astronomers to potential neutrino sources. This rapid response capability enables coordinated observations with telescopes. Around the world, IceCube's construction demonstrated remarkable international cooperation, with scientists from 12 countries contributing expertise and resources. The project required developing new technologies for polar operations, from specialized drilling equipment to robust electronics capable of functioning in extreme cold. These innovations have applications beyond neutrino astronomy, contributing to polar research and extreme environment engineering. The detector's success has inspired plans for even larger neutrino telescopes, including proposed detectors in the Mediterranean Sea and Lake Baikal in Russia. These projects build on IceCube's pioneering techniques while exploring different detection media and neutrino sources. In July 2012, IceCube detected something extraordinary. Two neutrino events, dubbed Bert and Ernie by the research team, carried energies exceeding 1,000 trillion electron volts, more than 1,000,000 times higher than any neutrino previously observed. These events marked the beginning of a revolution in our understanding of the high-energy universe and established neutrino astronomy as a powerful new tool for cosmic exploration. The detection of ultra-high-energy neutrinos represented a triumph of human ingenuity and perseverance. These particles carried energies impossible to produce in terrestrial accelerators, providing direct evidence of cosmic particle acceleration mechanisms operating at scales far beyond Earth-based experiments. The neutrinos' extreme energies indicated they originated from the most violent processes in the universe. IceCube's breakthrough came from its ability to distinguish cosmic neutrinos from atmospheric background. The detector's unprecedented size and sensitivity allowed researchers to identify neutrino events with energies so high they could only originate from cosmic sources. Lower-energy atmospheric neutrinos, produced by cosmic ray interactions in Earth's atmosphere, simply cannot reach the extreme energies observed in cosmic events. By 2013, IceCube had detected dozens of high-energy cosmic neutrinos, establishing their existence beyond doubt. These detections revealed that the universe contains powerful cosmic accelerators capable of producing particles with energies exceeding those achievable in any human-made device. The cosmic neutrino flux, while sparse, provides a new window into the universe's most extreme environments. The real breakthrough came in 2017 when IceCube detected a high-energy neutrino designated IC170-122A. This event was special not just for its energy, but for its timing and direction. The neutrino arrived from the direction of a known blazar, a galaxy with a supermassive black hole whose jet points directly toward Earth. This blazar, TXS0506+056, was experiencing a period of enhanced activity when the neutrino was detected. Within minutes of the neutrino detection, IceCube's alert system notified telescopes worldwide. Follow-up observations across the electromagnetic spectrum confirmed that the blazar was indeed flaring, producing increased emission from radio waves to gamma rays. This represented the first time a high-energy neutrino had been linked to a specific cosmic source, marking the birth of multi-messenger astronomy using neutrinos. The blazar connection provided crucial insights into cosmic ray acceleration. Blazars are among the most powerful objects in the universe, with supermassive black holes launching jets of particles at nearly the speed of light. The correlation between the neutrino detection and the blazar's activity suggested that these objects serve as cosmic particle accelerators, producing both high-energy neutrinos and cosmic rays. Further analysis revealed additional neutrino detections from the same blazar region over several years, strengthening the connection between blazars and neutrino production. These findings solved a century-old mystery about the origin of ultra-high energy. Cosmic rays, particles whose sources had remained unknown since their discovery in 1912. IceCube's discoveries extended beyond individual sources to reveal the diffuse background of cosmic neutrinos. These measurements showed that neutrino-producing processes operate throughout the universe, contributing to a faint but persistent neutrino glow that permeates space. This cosmic neutrino background provides information about the collective activity of all neutrino sources across cosmic history. The detector has also contributed to fundamental physics by setting limits on exotic phenomena. IceCube's observations constrain theories about dark matter, extra dimensions, and violations of special relativity. The detector's sensitivity to neutrinos across a vast energy range makes it a powerful tool for testing physics beyond the standard model. Multi-messenger astronomy, combining neutrino detections with electromagnetic observations, has opened new possibilities for understanding cosmic phenomena. When gravitational wave detectors like LIGO detect merging black holes or neutron stars, IceCube searches for associated neutrino signals. These coordinated observations provide comprehensive Views of cosmic events impossible to achieve with any single detection method. The success of IceCube has inspired next-generation neutrino telescopes. IceCube Gen 2 will expand the detector to 8 cubic kilometers, increasing sensitivity by an order of magnitude. Other projects, including KM3NT in the Mediterranean and Baikal GVD in Lake Baikal, will create a global network of neutrino observatories. These future detectors will enable neutrino astronomy to mature into a precision science. With improved sensitivity and larger detection volumes, scientists will catalog neutrino sources throughout the universe, mapping the cosmic landscape of particle acceleration and extreme physics. Neutrinos, once the universe's most elusive particles, have become powerful messengers carrying information from the cosmos's most extreme environments to patient observers on Earth. The journey from Wolfgang Pauli's desperate hypothesis to IceCube's cosmic discoveries demonstrates science's power to transform our understanding of the universe. These ghostly particles, which barely interact with matter, have revealed new aspects of cosmic phenomena and opened pathways to discoveries we can barely imagine.